Today, I'll be talking about stochastic gradient descent methods. And as you know, SGD methods, like Courtney mentioned, have been very popular in neural network training. And obviously, understanding the distributional properties of the iterates is important to understand the sort of training dynamics. But also, if you want to improve the current state-of-the-art methods, we want to understand how they behave distribution-wise. And in the recent years, we have discovered some interesting phenomenon about heavy-tailedness in the iterates and how this can affect performance. So today, I'll be talking about basically heavy tails arising in SGD. All right, so I think SGD is, I think everyone knows about SGD, but it has a few different ways of possible, so it can be implemented in a few different ways. So just to make sure that we're on the same page, let me sort of tell quickly what is SGD, right? So in the context of neural network training, essentially you have an input, you have an output. Maybe you want to classify images, right? And then essentially you have a loss function to minimize where x denotes the model parameters. So in the context of neural network training, these are your weights. I like x as an optimizer, but I realize that like a lot of communities use different letters. For example, W, some people like W. If you're a statistician, you may like beta, So I like x personally. And the data z is for example, in the supervised setting, it's the input-output pairs. And it's following an unknown distribution that, we have the data, but we don't know its underlying distribution. Right? That's why if I want to optimize this loss function, I cannot just do gradient descent because I don't know the underlying distribution. So the idea is to sort of resort to samples to sort of have a stochastic estimate of the gradient, if you wish. And obviously, if you were to change this loss function, this setup is known as risk minimization. And sort of if you just change your loss function, you may recover different problems. For example, if you just choose a quadratic, you may be doing linear regression where the aim is just to predict something linear. If you sort of choose the logistic loss, maybe you will be doing logistic regression. Sort of this setup is kind of very common sort of in the statistical learning. Okay. And as I mentioned, SGD in the setup means that you just have samples. Let's say here I am in the online setting, meaning that the data is streaming to me. It's the same setting I think that Courtney had. And then I'm just gathering B data points, averaging them as an approximation to the expectation, and then plugging stuff in. So for now, we will use a constant step size. But towards the end of the talk, I will look into different step sizes, like, for example, periodic step size, cyclic step sizes, Markovian step sizes, and so forth. Okay. So SGD actually works annoyingly well. So this is a very high-dimensional problem. You have millions of parameters. You run SGD, and things work out reasonable, right? So this is like, what's going on? Why is this method so successful? And if you understand it, maybe we can do better. So obviously, it's all about the noise, right? So if you think about where you will land up in SGD, the noise structure is sort of shaping the iterates. And how does the noise look like? Well, typically, you just assume that you have some IID data. So your gradient error, which is defined as the stochastic gradients minus the actual gradients, looks like an average of IID random variables that have actually zero mean in this case. So OK, average of random variables. OK, the classic limit theorem you have is central limit theorem, right? So essentially, if you assume that this sort of variables have finite variance or second moment, you could always use CLT that will tell you that, OK, the average, the gradient noise should look like a Gaussian random variable, right? And there are very famous theorems in stochastic optimization that tells you that, OK, if you just average iterates some way, you will find asymptotically a normal distribution. Okay? And actually, there are some nice properties about SGD, about optimal estimator type of properties that characterize this limiting covariance and says that it's one of the best estimators we can get, and so forth. So this is Polyak-Juditsky by the book. what's existing out there, saying that we have some sort of Gaussianity. Okay, so back in 2018, my colleague Umut Simsekli was visiting Rutgers, and we were looking into some experiments. If you try this Gaussianity behavior on a neural network, actually you see that it doesn't really hold. So this is actually an AlexNet. It has about, I think, 60 million parameters on some classification problem. Let's look at the histogram of the noise. So you look at the gradient noise and take norm of it. If things would be Gaussian, you expect to see, this is like a norm, so you expect to see something like a half normal distribution, and this is a logarithmic scale, so you expect to see something like this. Okay, but when you look at what's happening actually, in the first iterations, you see you have like a normal behavior, but as you run down the method, somehow the distribution becomes spiky with some sort of stuff that this looks more like heavy-tailed. Okay? So I was like, okay, for sure we have a bug in the code. We cannot submit this to any kind of place. There's sure a bug. So, but then, we tried this in the paper, you'll see. We tried it for many different architectures, data sets and stuff, and we always saw this sort of common behavior. And we were like, okay, we don't know why it is arising, but suppose that it does, sort of your gradient noise is heavy-tailed. What kind of limit theorem can we prove, or what can we say about the SGD? And actually, there's a generalized CLT that tells you that, okay, if your random variables don't have finite variance, don't worry about it. If you average them, you will just converge to a different universality class, meaning that you will converge to a different distribution. It's called alpha stable random variable. These are random variables that have like a heavy tail. So what's heavy tail? Any distribution that has sort of a heavier tail than an exponential. So if you decay slower than an exponential, you are heavy-tailed by definition. Okay? And if you look at this class, essentially, alpha equal to 2 is the Gaussian case where you have the finite variance. And anything less than alpha less than 2, means that your limit is sort of heavy-tailed with an infinite variance. Okay? So as you can see, if alpha is smaller, you have heavier tails and you are decaying slower. Okay? And in the paper, actually, we experimented with different networks, with different dimension and so forth. And when we estimated this tail index, we have seen something consistently far away from 2. Right? You see 1.4 here. Another thing that we realize is that when you look at the correlations between the generalization and the tail index, we saw like a positive correlation. So what is generalization? It's how you do on unseen data. Let's say you train a model, you have 90% accuracy on training data. If you try it on practice and see 50%, that means that you're not generalizing well. Right? So this is a different setting than Courtney's talk, because now I'm talking about generalization. And the methods that are extremely good for optimization are typically not good for generalization. Right? For example, stochastic gradient is a slow optimizing method, but it can generalize well. Right? So it's a different setting. And here also, I don't have any computing power kind of issues. But the underlying data assumption is the same in the sense that we assume that sort of we kind of run the algorithm. We don't think too much of data problems. All right. And and once we published this, we had some other papers in the field seeing this in different settings, like in GANs, attention models, and so forth. And this paper was awarded some sort of honorable mention for the best paper award for the discovery of this heavy tail phenomenon. Okay? Usually, there's no correlation between papers submitted and the reviews you receive. So I was surprised that they liked the paper. And okay, if you accept this, then you can also develop some nice continuum models that tell you that, okay, if you have heavy tails, then maybe you will be converging to some neighborhoods that have wider minima and so forth. So you can build a theory. But the problem is that we were making empirical statements. right? So we just tried a few networks. Can we do something more theoretical about this? All right, and in a similar work, I think, I wasn't here, unfortunately, a few days ago, but I think probably Michael may have presented some results about random matrix theory. The Martin-Mahoney papers also suggested that modeling the weights with heavy-tailed random variables can also help us to explain the training better. So here I'm looking at the iterates, but obviously you can see that it is related to the iterates, right? So if you have heavy tails in the gradients, the iterates will pick them up, right? So, all right. So essentially we have this kind of picture, okay? So, okay, generalization and heavy tails are correlated by lots of experiments we have. People studied how generalization depends on the SGD parameters like the bed size and step size. For example, a lot of people experimentally said that if you have very high bed sizes, it's not good for computation, but also it's not good for generalization, right? The problem geometry, meaning that when you find a solution, if it is in a flat surface, you can argue that maybe it's better for generalization because if you were to converge to a very sharp minima, you're sort of overfitting type of, which these are arguments you can make more rigorous. But for sure, there is some sort of relationship between generalization and the problem parameters, right? But this kind of links were missing in the sense that if heavy tails are sort of predictive of performance, like how the problem parameters depend on, how do they affect the tails? That's the question that you can ask, right? So, yes. Yes.
I'm not a statistician.
Right.
So how do you actually can you find the alpha? Like how do you empirically find it or something?
How do we find it?
Yeah.
Yeah, that's a great question. So first, we prove that the limit will be an alpha stable random variable.
Okay.
Then for alpha stable random variables, there are certain estimators.
Okay.
Right. So this is version 2.
Okay. Okay.
Version 1 was like, OK, just let's try to fit something. Right. But we can prove it.
You can, okay.
So we can, yeah. Which is the second part of the, yeah.
2 slides back, you had the distributional characterization for the ergodic iterate, right? The Polyak-Rupert average.
Yes.
So but I think your plots are for the last iterate, right? The alpha, this is for the last iterate?
No, it's like an average.
Oh, it is also average.
Yeah.
Right? So so when you talk about the alpha stable stuff, you're talking about the average iterate even for the neural net.
So there are a few different settings. So this experiment was on the last iterate.
Yeah.
But obviously, if you have heavy tails in the last iterate, and when you average them, you pick them up. Heavy tails is a bit like a disease. If you average something with something heavy tailed, you pick it up.
Yeah.
Or maybe, it's...
But when you're fitting it, this is still for the average.
Right, huh?
But when you're fitting alpha, you're looking at the average iterate.
Yeah, the reason for it is basically, The reason for it is that there are better estimators for alpha stable random variables. So when you average things, numerically you have more stable algorithms, okay? All right, so, and then there are lots of questions like, okay, how fast do you achieve this heavy tail regime? Can we have a more general theory of asymptotic alpha stability that would generalize the whole stochastic optimization literature, right? And for example, can we justify that? So another question is why are these tails rising over time? Like initially you are like Gaussian, and over time you become heavy-tailed. So why is this happening, and can we quantify this? Okay. And here what we did was, in our first paper, we were like, okay, let's stick to something simple. Let's think about linear regression. Is it something specific to deep learning, or is this kind of heavy tail something can arise in a simple problem like linear regression? It turns out that the heavy tails are arising due to the SGD dynamics. Something special about the dynamics. It's not necessarily specific to deep learning. And sort of linear regression is a setting where we can, a bit like Courtney's talk, when you have linear models, then you can analyze things, And then sort of we generalize it to more general nonlinear sort of models, right? Okay. All right. So let's go with the sort of linear regression setting. So you have the data A, output Y, and let's say that you are sampling, right? So gradient descent on a quadratic would give you something affine. But because you are doing something, you get a random recursion. This is called a random affine recursion, where essentially you go and sample from data. So your multiplying matrix looks like identity minus step size divided by bed size times something random. This is a random matrix, right? And then you have some sort of this MK, QK pair is essentially IID. And this is saying that your noise is also multiplicative and additive. It's not just additive, it is both multiplicative and additive, okay? All right, so what's the problem we're after? Essentially, we let let's say you fix the step size and the bed size, you let the algorithm run, and with constant step size, there will be some sort of equilibrium. You won't be converging because of the noise, you will converge to some sort of stationary distribution. The question is, what can we say about its tail behavior? Where we kind of look at the decay rate of the tail. So the alpha here is called the tail index. It tells you how fast your tail is decaying. Like if alpha is 10, it means your decay is like t to the 10. If alpha is 1, your decay is like, And in particular, if alpha is small, you will have, if alpha is very small here, right? Then you will have infinite variance. Okay? So it turns out that you can write down a nice formula for the tail index alpha. Okay? So there is as you can see, this is a function h. It has identity, step size, bed size, and the random Hessian in it. If you raise it to the power of alpha, this is the unique positive kind of integer, positive real number where things will be equal to 1. So in terms of the data distribution, for simplicity of this talk, I'm assuming things are IID Gaussian. So the idea here is to say that there will be heavy tails even if you have very light tail data. The extreme of it would be the Gaussian case, okay? And here I have a sort of a nice formula here, right? And for this to hold, we need some sort of condition, okay? And what is this condition? So essentially you have product of random matrices. There is something called the Lyapunov exponent that would characterize the growth of the matrix products. So this condition is telling you that basically your Lyapunov exponent isn't too big, so you're not like blowing up, okay? And it's kind of tight in the sense that if it's not satisfied, if it's greater than 0, there are examples where things will blow up, okay? And how do we do this? So, well, in queuing theory, when you go to a restaurant and wait a lot of times for some food, right, you don't like it. So people wrote down some limit theorem saying that I don't want to wait too much. So where people looked at like stochastic recursions, when there are arrivals and like sort of look at the stationarity. And then it goes back to the papers by Kesty and Golden about heavy tails. But that, we had to adapt them a bit to apply it to our setting. And then there's also another work by Michael and Liam. They also can show that heavy tails arise for sort of in SGD training. But I guess here we have like a much more explicit characterization because we look into sort of more specific models where in their work, there's some sort of lower and upper bounds on the tail index. Okay? And then you can also study some behavior of these tails. For example, if you decrease the bed size, you will have heavier tails, which makes sense, right? If you don't have too many data points, maybe things will be a bit rough. Right? And you can look at the sort of monotonicity with respect to dimension and so forth. And here, essentially, for the same network, the dimension will sort of lead to heavier tails in the setting, which is not in contradiction with Courtney's talk because I'm here in the generalization setting. So I can do whatever I want. I can increase the dimension. Okay. But this proves that, for example, smaller bed sizes will lead to heavier tails and so forth. And here's an interesting thing. There's a phase transition in the step size. So I'm an optimizer. So for us, we always do, OK, let's choose a step size tiny so that things don't blow up. That's what we do. We look at the second moments, we say, okay, choose the step size tiny so that everything stays in L2. Okay? It turns out that what happens is that there's a critical step size, which depends on the bed size, data variance, dimension, and so forth. If you cross this step size, yes, things blow up in L2, but they are finite in LP, where P is less than 2. And then if you try to push it further and further, there's like a sort of a phase transition where everything blows up, where the Lyapunov exponents blow up, basically, or become large, right? And and in the literature, we have seen things like, okay, use a large step size for training. This is related to sort of edge of stability, where you run your algorithm as if things are almost going to explode. And the theoretical explanation we have is, we are thinking of is that basically if you use these large step sizes, actually it invokes this heavy tail behavior, which will make your algorithm to explore the space better, right? And here, basically we have, we are sort of, connecting this result with some empirical results and sort of explain some of the sort of earlier observations. Then you can study the moments, say that, okay, the peak moment will be bounded by this. So obviously, if your tail index is alpha, only moments less than alpha will be finite. So then we can study how fast every moment blows up or stays bounded. And Wasserstein is a metric that I like. It's easier to work with, although hard to compute. So you can, it turns out that essentially you have a stationary distribution, and the speed you converge to this limiting distribution is also related to this fancy function h. But it's linear in this setting. So you really have geometric ergodicity, where you converge to a limiting distribution. There are some polynomial blow-ups in some moments, which is interesting to me, because for me, blow-up means exponential. So there are certain interesting things. But at the end, what we can prove is that if you average your iterates, you won't see anything Gaussian, but you will see something alpha stable. Right? So meaning that if you look at the averaged iterates, if you subtract and then divide by the right normalization, you will convert something to an alpha stable random variable. All right? So here, okay. And then we did a bunch of experiments to show that whatever our results are, so sort of numerical experiments just to verify our results. And more interestingly, we tried neural networks. So again, theoretically, the step size divided by bed size is correlated with heavy tails. So the question is that really the case? The theory is for quadratics. Is it the case in a neural network? And it turns out that you can also see this in practice, for a neural network. Okay, so basically the theory is somehow predictive of, of the performance in practice, right? Then I was like, okay, if the heavy tails is such a great thing, can we invoke it earlier? Why should we wait till the end of the training? So for example, this is like some example. Initially, you're like Gaussian, and then over time, you become heavy tailed, right? I'm like, can we invoke it? Well, we want to invoke it at the initialization right away. Just get into the business. How do we do that? Okay. Well, traditionally, actually, the initializations that people have are based on preserving the variance over the layers. Otherwise, things blow up or go to 0, right? So the question is, can we preserve a Gaussian random initialization to preserve, for example, the est moment, where s can be less than 2, right? If you can do that, basically, you will immediately invoke some heavy tails just from the beginning. Well, here, thanks to Chuck Newman, who wrote a nice random matrix theory paper back in '84, he wrote a paper about product of random matrices when they have Gaussian behavior. The entries are Gaussian. And then, thanks to this, it has some spherical symmetry properties, where you can write down things in a more explicit fashion. So as a consequence, thanks to Chuck Newman, we can really compute many things. And in particular, instead of, let's say, 2 over d initialization, that is for the typical let's say, initialization that's out there in the literature, let's say for ReLU activation, we have a correction here. If you want, let's say, s equal to 1, keep the first moment, you need to add some sort of correction to it so that, you are more aggressive with the initialization. Right, and of course, there are different activation functions, like there's leaky ReLU and so forth, and there are other things you can do, like dropouts and stuff. So for different settings, we have different results. But the thing is that in the deep network limit, meaning that if you have lots of layers, then you can show that also this is going to sort of invoke some sort of heavy tail in the iterates as well. Right? So this is initialization, but you can also look into the iterates. Okay. And then for different sort of, when you compare this with other initialization, you can see that there's a bit of gain. So the gain that we had in the training wasn't like a mind-blowing difference, but it's as if like we are having a better warm start. So we can sort of improve the generalization and accuracy a bit on different networks. This is great, but sometimes people tell me this is great, but here you have a constant step size. In practice, sometimes we use some other step sizes and so forth. So for example, one step size is the cyclic step size. In actual optimization, you can also prove nice stuff about cyclic step sizes, but here we were thinking of sort of understanding the cyclic step sizes, where you essentially you're on a grid, you go up and down. Then you can also, there are also people studied the random step sizes that are IID, right? So it seems like these step sizes can work better in some cases, right? But understanding the generalization is hard, so I'm going to try to understand the tail index. So if I can understand the tail index, then I can relate it to sort of generalization. So we are like, okay, I'm a mathematician, so we try to generalize. So let's try to generalize these things. So let's propose something like a Markovian step size, where it will recover IID, but it will also recover the cyclic step sizes, if the transition probabilities are chosen in the right way. And on this, for this class, we can compute the tail index and then compare which one will invoke heavier tails. And then you can also show monotonicity with respect to the bed size, dimension, etc., so to understand the effect of the parameters. But let me just give you a very simple idea. So the paper has more complicated sort of Markovian rules, but let's say for simplicity you have two levels. This is small step size, this is large step size. Cyclic would be going up and down. IID would be just like sampling in an IID fashion. And the Markovian would be you have a probability transition matrix P and then you play with it. And it turns out that, for example, you can actually compare all of the step sizes for this thing. And then you can argue that the cyclic and Markovian step sizes can invoke heavier tails. So basically, compared to the step size, if you use a Markovian or a cyclic one, you will be invoking heavier tails. And if you have a coarser grid, you will have heavier tails. Or if you have a wider range, you will have this heavier tails. So you could have the same expectation, but you could have a wide grid or a small grid, right? So basically, these results tie your step size scheduling to the tails. Okay. This is some experiment where you can see that the Markovian step sizes are invoking heavy tails. Okay. The ones that we are sort of proposing. And then when you go and try this on a neural network, in the paper we have like bigger scale experiments, but let's say this is the basics. What we see is that for the Markovian step sizes, there's no step size rule that will beat everything else for every experiment in the universe, right? So what we see is that in some experiments, this Markovian step size can work better, and just obeying the theoretical results we have, it will invoke heavier tails. But in some cases, for example, constant step size or the uniform step size may work better. So there's a correlation, but it's not like the correlation is not one, basically. Okay, and if I have 2 minutes, I could maybe finish something. Okay, this is great, and then you can argue that, okay, the data is not that centralized these days. If you think of collecting data with variables, drones or sensors, right? The data may not sit at the same location, where essentially you have these different nodes that are connected on a communication network. And you have maybe, there's no central planner for the algorithms. So a lot of times, actually, people would be running a decentralized algorithm, decentralized version of SGD. What it does is that you just have some data, and then you do stochastic gradient descent based on your data as a node. So you have also local variables, xik, where I denotes the node. So you will have some evolution that based on some local variables. But you sort of sync with your neighbors from time to time. Otherwise, everyone will do something independent, right? So this Wij is a mixing matrix that will take some sort of, it's a double stochastic matrix for you to take some sort of averages, right? And one common way is to sort of set up these weights according to the graph Laplacian. So basically, you will say, OK, let me do identity minus something proportional to the Laplacian. So if this parameter is 0, there's no communication. Everyone is doing their own thing. If delta is positive, then you're communicating. And the question you want to ask is, if we decentralize things, is it a good thing? What will happen to the tails? So think of a group of friends, right? If somebody is very slow, averaging may slow you down, right? But at the same time, when you average IID random variables, there's concentration. So it's not clear what will happen to your tails when you do averaging. Okay? All right. And here's a result where basically we said, OK, let's look at asymptotics in delta. If delta is positive, you are decentralized. If delta is 0, you do no communication. So let's have a formula for the tail index as a function of this sort of, we can do an expansion in delta if you wish. And then the formula looks a bit complicated, but essentially it all boils down to the signature of like a term here. If this term is positive, then you are heavy-tailed in the decentralized case. If delta is negative, you are lighter-tailed and so forth. And it turns out that there's a transition, there's a phase transition, meaning that if you have a big network or big step size, network effect will cause heavier tails. But if you have a small step size, maybe you are killing the noise so that the noise isn't that powerful, so that when you put a network, actually it's going to make you lighter tailed. So there is this sort of different sort of phase transition. And we can also compute a lot of stuff like what is the sort of thresholds and stuff depending on the network and so forth, right? All right, so I think I have 2 minutes. Right, thank you. So to summarize, basically the point we have here is that the heavy tails arise not because we are just doing deep learning, but in general, the SGD dynamics is such that for very general class of problems, your asymptotic or your stationary distribution will have power decay with some exponent, which we can compute for specialized models. In general, we have lower and upper bounds for it. But in any case, it's heavy-tailed. And how did we achieve these results? These are stochastic recursions. So for quadratics, it's a product of random matrices. So you need to get into a bit of random matrix theory. For general models, there are some theory about stochastic Lipschitz recursions by Diaconis and Friedman and others that we had to rely on. But overall, sort of we can quantify the dependence. We can sort of study the tail index as a function of the parameters, step sizes and batch sizes, sort of to relate these things. But I think there's more work to do about how tails are correlated with generalization. I mean, we see a lot of correlation, but is the correlation 0.9? Is it 0.8? So we need much more work in this direction. And also, the fact that invoking heavy tails can help with generalization, I mean, there's also a practical sort of benefit of studying these things besides doing some nice theory. I believe there's some practical algorithms that can be squeezed out of this type of approach. And then if you decentralize the data, it's not only helping with the compute, but also it can potentially help with the generalization because of the sort of, it's like, somebody may explore the space better than you, and if you do average with them, you can do better. It's like when you talk research about people from other fields, right? Like sometimes you feel like they're pulling you in some other direction, which makes you explore better. So the point is that decentralization can have something more than just computing power. That there's something more in terms of learning things together can really help you. Right? Thanks so much for the.
I have a couple of questions. First of all, thank you for the nice talk. So in terms of generalization, my first question would be, when you start to see heavy-tailed behavior, so there's some results that we have as well, that the number of catapults that you have in this catapult phase helps you improve generalization through a specific mechanism. Do you observe that when you do your techniques for cyclic learning rate, do you observe more catapults, and that's the reason you're getting heavier tails as well, and better generalization? Right?
So in our setting, let's say we see things getting heavier tailed over time because some moments blow up. So for us in this setting, maybe it is a bit more uniform. But I can imagine that if you think of SGD and if you look at, so here we are not looking at some particular paths. We are looking at the average of everything because we look at in distribution. But if we were to look into, okay, what happened with this run, what happened with this run, what happens is that when you increase the step size, it makes it jumpy. And the catapult phases are like when you just jump to another basin, you sort of start kind of being a bit blowing up like dynamics, right? So overall, here I would guess that if you were to look into particular paths, we could see more sort of zigzaggy kind of behavior. But here we do sort of in an expectation analysis, so we didn't see it. That's why. Yeah.
And the other question I had was, I was interested in, so you had another initialization scheme, I think,
yes,
some while ago, but it looked like you were increasing the variance of your initialization up front to induce heavy.
Correct. So, right. So basically, I mean, one idea is to say I'm going to initialize in the class of alpha stable distributions, or let's use Gaussian initialization, but step up the variance so that things are more explosive.
I just wanted your thoughts on, so typically I would expect to help with feature learning and things like this, you would want smaller initialization, but you were seeing better results with larger initialization here, so I wasn't sure how it related to that.
So this is basically if you want to invoke heavy tails, then this type of initialization can help you. But if you, for example, think of things like NTKs and stuff, usually you stay very close to your initialization. Are you thinking of that kind of?
I was thinking the opposite of not the NTK regime, but
okay,
the active regime. You want to extend the training time somehow, and I thought this would help you converge faster. Does this initialization push you? I would think it pushes you more into the NTK.
Yeah, I mean here we didn't study the convergence time, but you can show that in terms of optimization, it's going to slow you down.
Oh, interesting. Okay.
Well, let's say for strongly convex stochastic optimization, the rate will be 1/k. But if you have, let's say, heavy-tailed noise, you can prove that it's going to be slowed down, 1/k minus something. And that's because about numerical stability. To preserve, to avoid blow-up, you need to use a smaller step size. And we have a paper about that. So you're right. I think the heavier stuff, there's optimization and generalization. In terms of optimization, I think we see the same behavior that if you have heavy tails, then you may need to use a smaller step size just for convergence purposes. But this is more about not only convergence, right? So if you don't have to converge for this, as long as you explore, you're fine. Type of. But good question. Thank you.
Any other questions? We're about to take a break, and I guess we'll be back in about 20 minutes, 30 minutes for the last two talks of the day. Let's thank Mert Gürbüzbalaban.